So off of the homework, when we did this first one, I'm just going to explain the first step. What we did is we took the number of trials to find the expected value times the probability of success. And so that's how we ended up with an expected value of 1.2. What that means in this problem is if she is preparing, well, let me go back. If 1 out of 5 souffles that Sabrina prepares collapse, if she's making a total of 6 souffles, wouldn't you kind of expect that a little more than 1 would collapse? Doesn't that kind of make sense, the ratio that they're dealing with? And so that's why they say 1.2 actually collapse. 1.2 souffles out of the 6 will collapse. Now, that's the expected value. That's what we're expecting to happen. Obviously, 1.2 souffles cannot collapse. Okay, that's not possible. Do not round your answer right now. Keep it as a decimal for what we're going to do eventually. Then for the standard deviation, what we did is we took the square root of the number of trials times the probability of success times the probability of failure, and that's going to give us the standard deviation, okay? Now what happens is she's not going to always get exactly 1 or 1.2 souffles that collapse. It's going to have a range that it's dealing with, and this standard deviation is going to give us that range. So what it's doing here for this next step, it says something totally different on your worksheet. Can somebody help me out? What does it say on your worksheet again for the third question?
What is the maximum and minimum number of souffles Sabrina would expect?
Perfect. So what's the maximum and minimum number of souffles that Sabrina would expect to collapse? What we did this year is we changed this worksheet because we wanted to be more specific so you understand what we're actually asking, okay? So in order to get that maximum and minimum, we're going to take the expected value and we're going to add the standard deviation to it, and they're actually going to subtract the standard deviation from it. So what ends up happening is you get a maximum of 2.18 and a minimum of 0.22, okay? So the minimum number of souffles that would collapse are 0.22 out of the 6. The maximum number of souffles she would expect to collapse are 2.18. Does that make sense? It's giving us a range, a window to look in of what's an average for her. Okay, that's what we're working with today. We are also going to do this part, which involves calculating the binomial probability of something. And so I'm going to talk about that in just a minute. Okay. Now, when we access the notes are the same as yesterday, pretty much, except I did make a couple minor changes. I apologize if you opened the notes from yesterday, but they're not exactly the same. What I did is I changed all of the third questions so on each page. So I don't know, if you're accessing old notes, it might look a little different to you. Going back, these are the 2 definitions that we already talked about, the formulas, which you'll be provided with on the test. The last one we're going to use is this one. Okay, this is what we're using today. And you will also be provided with this on the test. But it's hard to know how to use it if you don't know what the variables mean. N still represents the number of trials, and the X is now represented the number of successful trials. Okay, so in that last one, the collapsing souffles, how many did we want to collapse? Such things like that. Okay, P is still the probability of success. Q is still the probability of failure. And so you know many of the variables already. The newest one is just the X. Okay. Now, so what we're going to do with this is we're going to actually calculate the probabilities of binomial experiments. Now remember, for a binomial, we have to have something where it only has 2 outcomes. It has to be a success or a failure, right? You also have to have where the probability of success and the probability of a failure add up to be 1. Okay, do you kind of remember talking about these things yesterday? I'm just trying to review it all. If you also need to know how many trials you're going to do. How many times do you roll the dice? How many times do you flip the coin? How many souffles do you make? Things like that, okay? Am I missing anything? Oh, independent. All the probabilities have to be independent. Each time you roll a dice, it's going to have to, this probably has to start over, okay? So each time you roll a die, if you're trying to roll a 1, the probability is the same if you roll the dice again and again and again, okay? What you have to be careful of is this, when it says without replacement, that's when the probabilities change. So let's go back to this problem that we did yesterday. It says 20% of the population is left-handed. and a group of 16 people are being observed, and it wants to know what's the expected value. So remember, for expected value, this is a review, what we did is we said we're going to take the number of trials times the probability of success. And in that case, we had 16 trials. The probability of a success in this case is being left-handed. And this is one of those, Brittany, that it's hard to tell which one is a success and which one isn't. So we're saying right-handed people, you're unsuccessful right now. No, you kind of get it, though. I remember from yesterday, this answer ended up being 3.2. What that means is, out of a group of 16 people, we're expecting that 3.2 are going to be left-handed. Now, it's not always going to be 3.2. There's going to be some error above and below, right? And that's what the standard deviation is going to give us. Okay. So it looks like this. And so I'm going to take the square root of the number of trials, probability of success, times the probability of failure. And I don't remember what that is, so we'll go ahead and enter it again. And this gives me an opportunity to give you one more reminder. Most of your calculators will not have a square root that continues over the numbers as you write them. So you have to be careful in that you want to make sure you enclose everything in parentheses. If you have a square root on your calculator that stops right there, it starts with a parenthesis, right? It's trying to tell you put everything in the square root within parentheses. So I get 1.6. So now this is the new part, you guys. What is the maximum and minimum number of people you should expect to be left-handed? What we need to do is we need to take, to find the maximum, we need to take the expected value, which is 3.2, and add the standard deviation of 1.6 to it. We also need to do the same thing for the minimum, except now we're going to take this expected value and subtract the standard deviation from it. So what we end up with is 4.8 and 1.6. So out of those 16 people, we can expect a maximum number of 4.8 being left-handed. We can expect a minimum number of 1.6 of those people being left-handed. Does that make sense? It gives us a range that we're dealing with. So this is the new part that we're just discussing right now for the first time. It says, what is the probability that exactly 3 people are left-handed? Now, so far, in all the things that we've calculated probability, we always had to divide by something. And in this case, you won't have to, which is kind of nice. To set this up, we're going to set it up using this. The total number of trials is 16. And the number of successes we want is 3. It gives us to it in this problem, right there. So my next step, I'm not going to write a multiplication symbol, but I'm technically multiplying between this combination and the next item. And the probability of success was 0.2. You can write it as 0.20 if that helps. And we wanted exactly 3 people to be left-handed. So I'm going to raise that to the power of 3. Now we also must multiply by the probability of being unsuccessful or right-handed. Okay. If we want 3 out of the 16 to be left-handed, how many out of the 16 are going to be right-handed? 13. And that's why it's asking you the n minus x here. Technically what you're doing. These two values will always add up to be this value. Okay? And these two values should always add up to be 1. Okay, that's what makes it a binomial. Okay, so now to actually calculate this is when you're going to put in your calculator. A lot of you, since we had spring break, have forgotten how to find a combination on your calculator, so I'm just going to remind you. I type in 16 first, and to get to the combination, I go to the math button, and I'm going to go over to probability. Okay, and then you'll see the third option down is the combination that we need. Okay. Now, you could just put in a multiplication symbol and skip all parentheses for entering all of this problem. I'm going to caution you on that. I want to try and get you used to putting all the information in parentheses, because if I give you the probabilities in fraction form, you will have to put it in parentheses. So we'll do an example where you see that as well. But that's why I'm putting it in parentheses. I'm trying to get you used to seeing it the same way for everything. to 13. Now what's beautiful is I hit enter, and that's my probability right there. I have nothing left to do because I use the probabilities in actually calculating it. So I have to divide by anything or anything else. So we have 0.24, I'm going to round it to 4 decimal places, which tells me I look at the I look at the fifth, and I ask myself, should I round that to up or down? Well, the 9 tells me to round it up, so I'm going to say 0.2463, and that'll be my answer. And this is good practice too, because on your test with binomial problems, it'll ask you to round to 4 decimal places. So you'll see this again, just like this. Let's do another example on here, and then I will do another example off your homework, okay? So the next one is this one. So you roll a fair die 5 times. If I remember correctly, when we did expected value, let me move some of this stuff up. There we go. So when we did expected value, our answer for this yesterday was 0.833. And then when we did the standard deviation, we got 0.833 again. I remember because those ones were the same. Okay? So this next question is asking, what is the maximum number? It doesn't care about the minimum. So what that tells me is, when I'm calculating this, I need to take the expected value, which was 0.833, and I need to add the standard deviation to it, which also happened to be the same thing. I don't know what that is off the top of my head. 666, okay. What that tells me, when you roll a dice 5 times and you want to try for 6s, the maximum number of 6s you should expect is 1.666. Yeah, go ahead.
They just not do a minimum on that one because it would just mean 0.
Well, that's not why, but typically what we'll ask you, like on a test or something, is what is the maximum or what is the minimum. Does that kind of make sense? They'll go one direction or another, and you'll see that in your homework too. Good question. So let's go over that new topic too. This is where we're going to use this formula. What is the probability of throwing exactly 2 6s? So out of the 5 throws, I'll speed this up. We want exactly 2 6s. And so the probability of getting a 6 is 1/6 of the time. Okay, see how I'm inputting a fraction now? This is when you would put in your calculator and you would need parentheses. This should happen 2 times is what we want to do. Otherwise, it's unsuccessful on the 5 other outcomes. And we want that to happen 3 times. Again, those 2 numbers add up to be the 5. So putting this in the calculator, I'll show you. So now I'm inputting it all into parentheses. Oh no, why didn't anybody stop me? Okay, now let's see if I can, okay, now we're okay. Okay, so I end up with this. 1.607, the 5 tells me to round that 7 up. So I get 1.608. Or point, I think I was saying that wrong. 0.1608. I guess I have the decimal in my place. Now I'm going to add a problem to this slide just to make it a little bit different. If I said, was a probability of throwing exactly 2 6s? Instead, what if I changed it? We have 5 outcomes. Was a probability of throwing 4, let's do at least 4 6s. Does that make sense to you? All those problems we've done previously, there's always been an at least, and you've always had to add in that, right? And that's what we're going to be doing here. Yeah, go ahead.
Instead of like putting those fractions in, couldn't we just like reduce them down before you do it too? Into the
Yeah, the problem with something like 1/6 is it's a repeating decimal. So I would like you to keep it in the fraction form. But let's say it's like 1/5, something that's equivalent to 0.2. I'm okay if you just make it a decimal. Does that make sense? So at least 4/6. What that means is I'm going to have to set up 2 chunks because out of the 5 rows, we could have 4 6s. And then I'd have to take the probability, not 2. This would now be a 4. And I'd have to add it to the probability of what if I got all 5 6s, which is a very, very small probability, but it could happen. What am I doing? Why am I writing 0 there? 5 6. Okay. That would be the answer for at least 4 6s. What if I said something, would you guys understand if I said at most 1/6? Do you guys know what at most means?
like it has to be below.
It has to be below. It's another way of saying less than. At most 1/6. I could either have 1/6 or no 6s. Yes, less than or equal to, exactly. 4 and 5? You would just add the 4 and the 5 together. Yeah, you could do that. Now, the reason why is Mrs. Wheeler bringing this up? Well, if you just look at your homework assignment one more time, you go to, and I'm going to erase this. What you're going to find is, oh my goodness sakes, at the very end, number 7 and 8. This one says at least 4. You're going to run into that. This one says at most 3 will recover. And what they're doing is they're adding several probabilities together. Okay, so I want you to be careful of that. And brothers, I want you to be careful of that too, is sometimes some of you don't quite get to the end of the worksheet all the time, right? And what stresses me out about that is whenever you create a worksheet in math, it always increases in difficulty. And so if you always skip the problems at the end, you're missing the most difficult ones. And maybe, I don't know, maybe you can plan on saying that on a test if you get what I mean. So like, think about that. I need to know what at least is. So before you leave, make sure you get everything and that part that's more difficult because that'll help you later on. So here's what I want you to do today. I want you to finish up the whole rest of this worksheet. There is a Dropbox for it, so you can Dropbox it if you finish it today. Otherwise, it's not technically due until tomorrow. So